Okay, so um, yeah, that's recording. So for us to actually study circular movement, so for us to study circular motion, there is one mathematics topic that I need you guys to understand first, and that topic is called polar coordinates. This type of coordinate system is super useful when it comes to circular motion. Why? Because circular motion always implies movement uh, with respect to an origin, movement in along a circle with respect to an origin. What you guys are normally used to is something called Cartesian coordinates. And this type of coordinate system specifies that you only need two values, let's call them x and y, to figure out where a point is lying within a two-dimensional space, right? So if we have our origin, so let's put our origin here, okay, and call this axis y and call this axis x. Given this pair of numbers, I can locate any point within this infinite space, right? So a point here would have coordinates x1, comma y1. A point here, for example, would have another pair of coordinates x2, y2. Another point here, for example, would be x3, comma y3. So this coordinate system, Cartesian coordinate system, you need two variables, x and y, in order to figure out a point within the space, okay? X would be the distance, the horizontal distance from the vertical axis, and y will be the vertical distance from the horizontal axis, okay? That is basically what this coordinate system is. I'm going to repeat myself here. So x represents the horizontal distance from the vertical axis, so this is x, and y represents the vertical distance from the horizontal axis. Okay, so this is y right here. Okay, that is how we figure out any point in space. Now, for polar coordinates, okay, for polar coordinates, we also are going to have an origin. Okay, but in this case, the origin, we can draw it exactly as our xy coordinate system, our Cartesian coordinate system. But now for this coordinate system, we're going to be using two different variables called r and theta. And just like in Cartesian coordinates that we could use these two values to pick any point within space, we are going to use these two variables to find any point within space, right? In polar coordinates, this coordinate system doesn't have names, okay? Why? For example, if I want to figure out where this point is with respect to this origin, okay? Instead of measuring this distance and then this distance, what I'm going to be measuring is the distance from the point to my origin, okay? So this would be r, okay? The distance from the point to the origin. And with only a value of r, I could have any point within this circle. Oh, that's a horrible circle. So imagine that that's a circle. So if I only specify r, my point would be along any point within this circle. So I need to specify an angle at which that point is. So I specify this angle right here. Okay, so given some radius and given some angle, I can specify where my point is at any point in the universe, right? So if I specify, for example, this other point right here, okay, the coordinates for that point would be the value of r, and so let's put r here and let's put it in red. So this value of r, radius, and this angle right here, theta. Okay, R2, theta 2. So I can locate any point in the known universe. So for example, I could also say I want to figure out this point right here. So for that point, I would locate it with this value of R and whoop, that value of theta. Correct? So that is, in essence, polar coordinates. Polar coordinates are super useful. Why? Because since we are moving along a circle, okay, normally we can track position. So since we are moving along a circle that doesn't change radius, we can track the position of a particle. We can track position of a particle with just the value of theta. Okay, so at any given point, so let me put a new layer here. Okay, so let me draw a circle. This will be hand drawn, so sorry. Okay, so at any given point at any given moment, my particle is always inscribed within this circle, correct? So that means that if I take this as the origin right here, and I'm using polar coordinates, my R1 at point, so this is point 1, and this would be, let's see, point 2. So R1 and R2 are equal, okay, because I am moving within a circle and the radius of the said circle doesn't change. So how can I pinpoint where my actual particle is? Well, with just the value of theta, right? So as you'll get to see in circular motion, okay, as we get to see in circular motion, the way that we track displacement, so the way we track displacement will be with theta. Okay, so in 1D motion, displacement was in x or y. Okay, in 2D motion, it was a combination of these two. Okay, remember? Circular motion is also one dimension, just that this dimension is circular. Okay, we are not moving along a straight line, we are moving along a circular path. So technically we only have one dimension, we only have one degree of freedom, and that degree of freedom will be theta. Okay, we can move if we're moving along one dimension, okay, so it would either be the horizontal dimension, so we could go left or right. For the vertical dimension, we could either go up or down. For our circular displacement, we can only move theta, okay? We can't move away from this circle. We can't move inside this circle. We are moving along this circle only. So it's only one dimension. And the way that we can establish at what point we are is with this value right here, theta, okay? So that is going to be very super important when we are taking into consideration acceleration, okay? Because, and I'll just introduce the topic briefly here. In one-dimensional movement, we have one-dimensional velocity and acceleration and whatever. When we're talking about circular motion, we'll see that velocity, instead of having this as linear velocity, we are going to have something called angular velocity. And instead of acceleration, we are going to have something called angular acceleration. And as we'll see, we'll be using the exact same formulas that we used before, but now we are taking into consideration angular quantities. Okay? And that is basically it for this video. I'm going to just finish this. Okay? And with these two equations, I could pinpoint at any given point in time where my particle is along this one-dimensional object, which is a circle. Okay? So if there are doubts, please feel free to ask them, and I'll see you in class. Thanks, guys.